So, hello everyone. So far we have talked about the mathematical formulation within continuum mechanics. So we introduced the balance equations, the constitutive equations, and the kinematics. Now we assume that these equations are found in a software like finite element software, Abacus, ANSYS, or Flex PDE, and we want to solve a boundary value problem. What would be the challenges which are connected to these implementations? So today we'll talk about the convergence in finite element analysis. So I assume in this video or in this like lecture that you have a background of finite element of computation. I think many of you have attended the course of finite element method, and they know what we mean by, for instance, shear functions, what we mean by elements, and so on. So we'll talk a little bit about the convergence in the finite element simulation. And one of the very important aspects is the mesh convergence. We'll talk about the H and B mesh refinement. So for instance, to improve the accuracy. Convergence in presence of singularities. So this is also a very important issue. Convergence of is the presence of lacking. And we'll talk finally about the qualitative measurement of convergence. So, as I said, in this part, we will address a number of issues which affect the convergence and accuracy. Thus, it affects the reliability of our finite element model. So what do we mean by mesh convergence? So one of the important aspects in computational mechanics that affects the accuracy is mesh convergence. In other words, the mesh size or mesh should be refined or should be fine enough so that the solution will be independent or becomes independent of the mesh size. How do we do this? Let's look at this example. For instance, we have here a beam which is clamped from one side and it's loaded by certain load at the top of it. So it's like distributed load. And we look at the different responses at the point A in this structure. And for instance, the response at point A could be the displacement, it could be the stress or the strain. And assume that we know the solution. So we'd have like an exact solution if we have maybe analytical solution of our equations, or if we have a reference solution. And then by mesh refinement, if we increase the number of finite element, in this case, we would have convergence to a certain value. In the mesh refinement, there are certain steps which we can follow in our computation to make sure that that the mesh convergence is really applicable in our problem. So the steps in checking the mesh convergence: first, we identify the quantity of interest. This could be the displacement, this could be the strain, the stress, and then the quantity of interest starts to converge to a particular value. So by increasing the number of elements, we will see that we will have only slight changes after increasing the number of elements. So if two subsequent mesh refinements, they don't change the results significantly, so we'd have a very, very slight change, then we can assume that the mesh has converged. So as a side remark, a good model or in good models, it's important to find a trade-off between the accuracy and mesh size, because increasing the number of elements, in this case, you are increasing the number of your unknowns or number of equations which you have to solve at each time step. So this would increase the computational costs very much. However, if you reduce the number of elements, so you improve the, let's say, the speed of computation, this might also affect the accuracy. So we should find a balance between how fast our solution is and how accurate it is. And this is what I mean by this trade-off. We have some scheme to increase the number of elements in order to improve the accuracy. So in general, it's necessarily that the mesh, as I said, is the entire domain be fine enough to get accurate solution. However, applying finer mesh in certain regions with higher stress concentration rather than applying very fine mesh to the whole domain, it helps first to improve the accuracy. However, it also would not affect the computational costs that much. So I will give here an example to this. So this is from one of my projects. We have this domain. Let's take it as a two-dimensional domain. And we have loads on this. We see here the sigmas, the stresses applied on it. This is a hydraulic fracture example where we have here a notch or a place where we inject fluid. And then we expect that there will be a crack. So crack will be associated with stress concentration, or where we would need like more elements, we would need fine elements. But far from the crack, for instance, here and maybe in the bottom, we don't have a crack. We would have purely elastic behavior. Then we would not need a fine mesh. What we do here, we choose like coarse mesh far from the like region of interest, where we expect the crack to propagate. And we apply very fine mesh at the place where we expect the crack to happen. And we see here's the crack path. We have a very like a smooth path. And we did not extend the computational cost to a very to an unacceptable range, because if we apply this fine mesh everywhere in the domain, it will be very much more expensive. There are some like theories behind this. So according to Sand-Winant's principle, the local stress, so stress is a local quantity. So the local stresses in one region of certain solid materials, so in some location in our domain, they don't affect the stresses in the other regions. So that's why we can refine the mesh in certain region and leave the mesh very coarse, like far from the region of interest where we don't have maybe stress concentration. There are like several ways how to make the mesh refinement. This could be also automated mesh refinement. We call it mesh adaptivity, but you can also apply it like by hand. So you make the refinement before you start the computation. If you, from your experience, you know where exactly or where approximately the stress concentration will be. There are like two options. So let's assume this is our domain, and we discretize this with 4 quadrilateral elements as initial, so linear elements. You see here 4 nodes. And we figured out later that we would have like stress concentration in this region. So in one of these segments, first option is to increase the number of elements. This is called adaptivity. So, it's adaptivity if it's automated, but you can do it also by hand. So in this case, we are reducing the element size. In other words, we are increasing the number of elements because the domain is already predefined. This is the preferred way of overcoming this challenge of stress concentration. There's another way is to increase the order of the elements. So here we have quadrilateral elements, linear. We can replace them by like quadratic shape functions. So we put nodes in the middle. We could have also cubic shape functions. We have more nodes. So we increase the order of elements so we can capture more like stress concentration. Most of people go for this option. Because here, for instance, you would have quadratic elements in one element, then you are forced to make the other elements of the same order. Otherwise, you would have some kind of incompatibility. So, or you make both of them, so you increase the order of elements and you increase the number of elements. This would be also fine. Important here is to have mesh convergence. Okay, so this is what I already talked about is related to mesh refinement in connection maybe with some stress concentration, but sometimes the geometry itself, so how the geometry look like, it maybe force us to choose fine elements. Take for instance this this geometry here. So we have a plate with a hole in it. And we assume that we have like a load on it, which is this load is is not so extreme, so we don't have really stress concentration. So initially we don't really need a lot of elements. We can choose only a few number of elements. Let's choose this initially. So we choose big elements. We can make a mix of quadrilateral and triangle elements. We see that here, if we choose this coarse element, we are losing the geometry of the circle. So our circle would be in this like very rough mesh. It would be like a square. So this is not good. So this geometry will force us to choose finer mesh. And I block this with my hand. So we would have maybe, instead of 4 elements, we'd have maybe here, I don't know, 20 elements, so that we can capture the circular shape of the circle. So this is to capture the geometry. But this is, as I said, it's not necessarily connected with concentration of stresses. Okay, so now having talked about the mesh convergence, we can now move to the second section, which is a convergence in the presence of singularities. I will give here 2 examples to illustrate what do we mean by singularity. So for the first example, consider like a structure, which is like a beam subjected to uniaxial forces. So F here. And this is our conceptual model. So if the cross-section of the beam has an area of A, then the stresses will be sigma F to A to be a uniform stress. And then your task is to build a finite element code, so to model this beam as a solid element. And the question is how to apply the forces, in this case, in the model. So in the finite element numerical model, we can replace this force as one option by distributed load at the boundaries. You see here directly that like opposite to the boundary, we'll have the stresses inside the material. So the stresses will be our internal forces, and they are finally and nicely distributed. This is one option. The other option is to put the force directly at the boundary. So you pick up like a point, maybe in the center, so at the axis of our beam. However, you see here at the boundaries, because we have the force which is carried out by boundary elements here, let's call this as A dash here. So the force, the stress at the boundary would be sigma dash equals to F divided by this area at the boundary. And at this boundary, this sigma dash would be much bigger than sigma, which is inside the domain. So you will need to move a lot from the boundary to the inside the domain to get this uniform distribution, where in the reality we would have a uniform distribution. Now, maybe you think, okay, let's think about this, the problems. Okay, we have finite element, let's go for mesh refinement. Now, the bad news, if you go for mesh refinement, so this A dash, which is at the boundary, it's become even smaller. According to this relation, sigma dash will be even much bigger. And at some point, if you go for very fine mesh, then this stresses at the boundaries will become infinite. And this is a kind of singularity, so it will not help, it will not converge. So the solution will be, in this case, to go for distributed load. So this is a right model, and this is a wrong model. So you should be careful about this. And a second example, which is also very famous here, so the clamped beam with a support. So we have a beam here, it's clamped here, and we have this support. Maybe in civil engineering, this would be a beam, and this would be a column. And what we are interested in is the mechanical behavior of this beam. Now we go for finite element, and we want to model this beam as a solid material. So we choose certain mesh. First option is to replace this support by 3 fixed nodes here in the vertical direction. So we put a support with finite links. And some people go directly and put only one point, so as pin support at one point. And this is B is a distributed load at the top boundary. Now, the numerical solution of point support with concentrated reaction force, it leads to singularity in stress and displacement. Exactly the same problem as before. We would have very, very high stresses here. And this error will accumulate to the rest of the domain and will give us like a bad solution. So no or bad convergence is obtained via mesh refinement. So refining the mesh will make the stresses at this point even much higher, and then we'll have maybe the whole computation will stop. It will not run. Again, this is the best or this is a better model, and this is a bad model. So you should like be careful about this. Some software, like especially the softwares which have interface user interaction, even if you put such support in the background, you'll have some post-processing steps. So they don't give the support to a certain point. So they distributed this in the background. So maybe you'll wonder, okay, I already gave, for instance, bin support, still it was running. Yeah, because the software developers, they understand this problem and try to overcome this. However, if you develop the software yourself, then you should be aware of such problem. Now, in the presence of singularities, this is like a quantitative illustration, increasing the number of finite elements or mesh refinement, it leads to increasing of the stress towards infinity and not to the reference value. So we said in the context of mesh convergence that the solution will converge to a nice result, to a reference results which we have maybe validated or we have a analytical solution. In the presence of singularities, we see that the solution goes maybe to infinity, which is not good. So we have to check the supports, as I said. The second problem, which is which I want to talk about, is the convergence in the presence of locking, which is a different type of problem. Locking is the opposite of singularity from the sense that the results which you will get here, they are less than the real one. So let's also give an example. So consider a cantilever beam, which is a beam fixed from this side, clamped, and we have pure bending. So we put a moment here and consider this beam to be slim. So we have a thickness of T. Under some circumstances, the displacement calculated by the finite element method, so we will explain what are these circumstances, are of orders of magnitude smaller than the reference values. So we have locking as example in conversion with the analytical solution. Why we get this? So the elements are said to be locked, so the stiffness in this case is overestimated. So if we recall this example here, or let's say first that most of common types of locking are the shear locking and volume locking. So shear locking is connected to the geometry and the type of elements that we are using. And the volume locking is connected to the material parameter. So don't be surprised if you, for instance, change the material parameters sometimes and you are not getting convergence, because we would have also a volume locking. Let's talk about the shear locking. It happens, for instance, when using linear elements in the pure bending of thin structures. And for instance, if the thickness is very small, let's have a look at this cantilever beam. If we can divide this into small segments, and then we see this moment which you apply here, and this is the thickness. In this case, the elements are unable to capture the kinematics of deformation. This is a finite element. Let's have a look at the analytical solution using the Euler-Bernoulli beam. So if we take the beam or a segment of the beam and we put M here on the right-hand side, then we have the reaction also M on the left-hand side. This is a bending moment, and we see here directly that sigma 1, 1 will result inside this beam. And it is non-equal to 0. It's maximum at the top and the bottom, and then it will be 0 in the axis. And we will see that we have no shear forces. In this case, clearly we have only bending moment which is applied, it means that the sigma 1, 2 with the shear stress would be also equal to 0. So this is the analytical solution. It's correct solution. Now, if we move to the finite element, and we take like one element for the whole height of the beam, and we choose linear quadrilateral elements. You see here 4 nodes, and we take full integration. So we have these Gauss points here. I'm pretty sure you know what I'm talking about. And then we apply the forces here up and down, which result from these moments, which we applied at the left and right hand side. First, as a note, the linear elements, they cannot capture the curvature of the real structures. That's why we have here straight lines up and straight line down. Under bending, we have redundant shear stress occurs. So first, the sigma 1, 1 would not be equal to 0. So this is what we would like to see. However, the sigma 1, 2 would also not be equal to 0. You see, corresponding to this Gauss point, we would have some kind of deformation. It means that the additional shear stress component, which is not equal to 0 here, it causes the elements to reach equilibrium with smaller displacement. So due to the deformation, we have a certain amount of energy. A part of the energy is now connected to sigma 1, 1, and we have this redundant energy connected to sigma 1, 2. It means we have a stiffer behavior. The bad thing about this, you would not notice in the code that you have this kind of this locking, because you had very nice convergence, but the behavior, you'll have no convergence problem. You cannot see it, but the total behavior will be stiffer. A possible solution is first to use higher order finite element, mesh refinements, and maybe play around with the integration. So for instance, in this case, if we choose one Gauss point, which seems to be less accurate, however, we would you'll get rid of the sigma 1, 2 as well. However, most of the time you'll use more elements and higher order finite elements. The second kind of locking is the volume locking. This is very important. It occurs when the material is incompressible. Incompressible material is corresponds or it has Poisson ratio, which goes to 0.5. Take for instance under plane strain assumption as an example, where we have the epsilon 3, epsilon 1, 3, 2, 3, all of them are equals to 0. In this case, sigma 2, 2 can be written in this form here. Now, if we take first like compressible material, just like any material, then this epsilon will be 0.2. It shows the elasticity parameter, any value, take it 1. Then you will get this solution for sigma 2, 2. However, if we take incompressible materials, if I tell you the material is completely incompressible, so we would have nu equals to 0.5. Put this 0.5 in the relation of sigma 2, 2. You will see that you'll have infinity multiplied by epsilon 1, 1 plus infinity multiplied by epsilon 2, 2. So you'll have a very stiff behavior. I will tell you that the finite element code will stop, it will not converge. Of course, then you should avoid putting this extreme case. I mean, if you are like solving real problem, there are no material which has a nu equal to 0.5 exactly. Even the stiffest materials, they have some compressibility. So you'd have like 0.499, for instance, which might help you to avoid this case. But you should be aware that this volume locking is a serious issue. And don't be surprised if you change the material parameter and you are not getting convergence, because this could be one of the problems. Now, how can we measure the convergence? Now we have to talk a little bit about the errors. So in the presence of analytical solution, so in other words, if we know the true solution, the errors of the numerical results can be measured as follows. So you can measure the errors in the displacement. So if you have the analytical or correct solution minus the numerical solution, you would know this deviation between the true and the numerical. You can measure the errors in the strain, and you can measure the error in the stress. And you see here is the errors. In this case, they have, this could be vector, this could be tensor, and this is tensor because the displacement, strain, and stress, they are tensorial quantities. Now, if you are like solving a real problem, of course, you would like to see the errors going to zero. So for any discretization methods like finite element methods, finite volume methods, finite difference methods, and so on, mesh convergence, it requires that these errors go to zero, so you'll never get zero, but they should be close to zero if we refine the mesh. Of course, the mesh refinement, the mesh size, if you have one-dimensional elements, then it's easy. So H is simply the distance between two nodes. If you have two-dimensional elements like triangle or quadrilateral, you can draw a circle and then take the radius or the diagonal of this circle, and this would represent the mesh of the elements. Now, as I said, the errors which I presented here, they are vectorial or tensorial quantities. So what we want to see, we would like to see a number which represents errors. So norms of errors can be defined such that the averaged errors over the entire structure or domain can be calculated. Also, this is important because if I go back to this is displacement at each node of our finite element mesh. However, we discretize the domain. So we'd like to see an error which is related to the whole domain of our finite element computation. That's why we are interested in the entire structure or domain. That's why we would include also integration in the computation of the error. Just a side remark, if you have a vector, for instance, as an error for the displacement, you would have, for instance, the first norm. It's simply the first component of the error, so the norm of the component plus the second, norm of the component. And then we'd have a second norm or LT norm where we have square root of the square of the first component plus the square of the second component. This is as a side remark. So in this case, if we want to compute the displacement errors over the whole domain, what we do here, so it's L2 domains. First, we have integration over the whole domain, error of displacement, scalar error of displacement. So this would be a scalar quantity. It's something similar to here. And we take the square root. So it's called the L2 norm of the displacement error. You can apply this also to the stress error. So it would be L2 norm of the stress error. Then we have the energy norm called sometimes a epsilon, so E epsilon, then we have norm and have E here, so E refers to energy. And then we have the integration over the domain. You see here we have the errors of strain, scalar, C is our elasticity tensor multiplied by epsilon, by E epsilon, which is the error of sigma. So we have error of strain multiplied by errors of sigma. Strain multiplied by stress will give us energy. And this is over the whole domain, so it's the energy norm. You have also sometimes H1 norm, which will be, for instance, which includes the errors of displacement, errors of strains, and there are like several definitions of error, so I just introduced these as examples. And in practical application and also in the software which we are applying, it's the FlexPDE, we have the non-dimensional root mean squared value of the norm, which is defined, for instance, as this in this relationship. So this is also an option. The important is that at each time step, we would have one value for the errors in the whole domain. And not only at each time step, actually at each iteration, because we apply iterations so that these errors become converged to zero. It will not be zero. We put like a lower limit for the errors so that the iterations keep going on until we reach this minimum error. So I mentioned, I think, in the first lecture, one book about the finite element code and the connected challenges. So I would refer to this again, this book from Zinkiewicz and co-authors, The Finite Element Method, Its Basis and Fundamentals. There are also several publications and books in this direction. So where you can go for more details, but also you'll find a lot of useful information on the internet. So with this, I'm at the end of this video. Thank you so much, and we will meet each other on Monday. Thank you so much.